Hello everyone to this lecture about the probability distributions in the case of continuous random variables. So we will start by the uniform distribution. We say that a continuous random variable x is uniform on the interval AB if it has a PDF of x equals a minus b minus a if a less than x less than b, so a in the interval AB, and 0 otherwise. And it is easy to get this PDF because once we have a and b, we can get it easily by 1 over b minus a, and 0 for the case where x isn't in the interval AB. And its graph is like that. So if we have an interval AB, so we will have 1 over b minus a, so here and here, and it will be like that. So it is a continuous random, and it is 0 otherwise. So 0 for x isn't in, when x is not in interval AB, it is 0, and it is 1 over b minus a in this case. And it is different from the uniform that we have seen that may confuse you. We have seen it in the secret case. We have seen that the PMF of the PX of it is 1 over b minus a plus 1, and its graph is like that. So it is like that, have the same 1 over b minus a plus 1, but this is for the discrete random variable and isn't in our case here. So the case of a continuous random variable, the uniform distribution is defined by this expression. The CDF of the uniform distribution in the case of continuous random variables is integrating from negative infinity to x of fx dx. So it is equals 0 for x less than or equals to a, and x minus a over b minus a for x between a and b, and 1 if x is bigger than or equals to b. And its graph is given by like that. So a b can be any value, so it can be negative, it can be 0, it can so they don't have to be positive. For example, one of them can be negative, one can be positive, or both can be negative. So its graph is like that. So it is 0 for x less than or equals to 0, and it is linear here, and it is 1 here. So it is linear between a and b, and it is 1 after b. This is the fx, the CDF of the uniform of x when x is a uniform random variable, and its expectation or its mean is given by b plus a plus 2. It will be its expectation will be here between a and b, and we can get it easily by integrating from a and b of x fx dx. So we replace fx here with this 1 over b minus a, and we can get this easily. And its variance is also b minus a squared over 12, and we can get it also from this expectation. We know that it is equals e of x squared minus bx or squared, and we can get it easily from this expectation that we get from the PDF. The next distribution is the exponential distribution, and we say that a random variable x, a continuous random variable x, is exponential with parameter lambda if its PDF fx is given by lambda e minus lambda x if x bigger than or equals to 0, and 0 if x less than 0. So this is its PDF, and its parameters by this lambda, and its graph is given by this. So here x, and it looks like that. It converges to 0, and its CDF if fa equals p of x less than or equals to a, and it's given by e minus lambda a for a bigger than or equals to 0. And its expectation is 1 over lambda, and its variance is 1 over lambda squared. And it is important here to note that lambda is control how fast the curve is. For example, if lambda is a big value, big number, so it will converge fastly. However, it is a small number, it will converge slowly, so it will take a lot of time to converge. Now we will talk about one of the most common distribution in life and in engineering. So it is useful in engineering. It is the Gaussian distribution or the normal distribution. And we say that a continuous random variable x is Gaussian random variable with parameter mu and sigma squared if its PDF is given by 1 over square root of 2 pi sigma e minus x minus mu squared over 2 sigma squared. And we note it as x is in the normal distribution of mu and sigma squared as a variance. So the curve of the Gaussian distribution is look like that, so it is a bell-shaped. So if we have mu here, symmetric about mu, so it is looks like that, and its value here is mu minus sigma, so it is here sigma, not sigma squared, and it is a standard deviation, and here is mu plus sigma, so this value, and in this value it is mu plus 2 sigma, and here it is mu minus 2 sigma. And the expectation of a Gaussian random variable is mu, so its mean is its expectation, and its variance is sigma squared, and the standard deviation is sigma, square root of variance, it is sigma. And it is difficult to get the CDF directly from this expression because the CDF is fx or fa equals integrating from negative infinity to a of fx dx. So it is difficult to integrate this expression. So there is a method to get it easily that we'll see in the next slide. But before I show you how to get the Gaussian CDF, let me define the standard normal random variable or standard Gaussian random variable because I will need it. So we say that x is a standard normal random variable if its mu is 0 and its variance is 1. So we say it's that 1 mu is 0 and its sigma squared is 1. And in this case, fx, which is the PDF, will be, of course, x is a standard normal random variable, will be equals 1 over 2 pi, so square root of 2 pi, sigma squared, sigma is 1, so sigma squared is 1, sigma will be 1, so it is 1, e minus x minus mu squared, so mu here is 0, so it will be x squared over 2 sigma squared is 1, so it is so fx will be 1 over 2 pi or square root of 2 pi e minus x squared over 2. And we can get the fx here, which is the CDF of this x when x is standard normal random variable. We can get it easily from this expression by phi x. We know it's phi x equals 1 over sigma squared integration from negative infinity to x of e minus y squared over 2 dy. We use here y because just we don't want to confuse you by x here and x here. So this is the phi x, which is the CDF of the standard normal random variable, and we will see how to use it to get the CDF of any Gaussian random variable. If z is a standard Gaussian random variable, so its mean is, so z will be in have mean 0 and variance 1, so this is z, and x is any Gaussian random variable, so with, of course, x is with parameter mu and sigma squared. So x will be in n mu, any mu, and sigma squared, any sigma also. So in this case, we can write z as x minus mu over sigma. And the CDF of x, we can get it by fx of equals px less than or equals to a, and we can here subtract by mu here and mu here, so it will be just x. When we subtract by mu here and mu here, we'll get x minus mu and a minus mu, and as sigma is positive, when we divide also it will be the same when we divide here and divide here. And when we look to this, when we look at this expression is the same here, so we will get here p of z less than equals to a minus mu over sigma, and this is a constant value, so that means we get the phi, which is the CDF of the standard normal random variable, and we can get which is phi of a minus mu over sigma. So we now get the phi of a minus mu over sigma, and we know to compute it, but we usually get the phi of any value from a given tabular that contains all non-negative value of x. So all of this tableau I will show you now is the non-negative values of the random or the standard random variable. This is the tabular. So for any value of x, we'll get this value from here. For example, if we want to get the value of phi of 0.7, for example, we look here for the 0.7, it is here, and after it is at 0, so it is in this case, so it is this value. This is a value of 0, it is 0.7580. So this value here. And if, for example, we want the value of phi of 1.43, for example, so we look here, 1.4 is here, and we look to this 3, which is the second number after the point, so it is 0 here, so we look at the correspondent here is here, and we get the value of this phi, which is 0.9, which is here, 9236. So this is how to get the value for the phi of non-negative values. However, if we have a negative value of x, we will get it by phi of minus x equals 1 of phi of x. For example, if we have a phi of minus 1.43, that we compute here 1.3, it is equals to 1 minus phi of 1.43, which is 1 minus 0.9236.